Welcome you all to the video practical series. Here we'll perform the experiments related to the different laboratory subjects. Today we will perform the experiment of the subject Digital Signal Processing Laboratory. The title of the experiment is Verification of Sampling Theorem. I am Professor Amit Kumar Patil from Department of Electronics and Communication Engineering, School of Engineering and Sciences, MIT Art Design and Technology University, Pune. So let us come to the experiment verification of sampling theorem. This experiment we will perform on MATLAB software or tool. First, let us come to the lab manual of the experiment. Then we will perform it. So, aim is to verify sampling theorem. So, sampling theorem, this word has been derived from the word sample. Sample is a piece of data taken from a continuous time signal. Sampling theorem states that any continuous time signal can be sampled into a discrete time signal and it can be recovered back if the sampling rate is greater than or equal to twice the maximum frequency of the signal. That is, Fs is greater than equal to twice of Fm, where Fs is the sampling frequency and Fm is the maximum frequency of the signal. So we can sample a continuous time signal into a discrete time signal and also it can be recovered back if this condition is satisfied. When sampling rate becomes exactly equal to twice the maximum frequency of the signal, it is known as Nyquist rate. And the reciprocal of the Nyquist rate is known as Nyquist interval. So to sample a continuous time signal, this continuous time analog signal is multiplied with the periodic impulse train in a multiplier and the output is a sampled signal. So here also we can see in the form of waveform, analog signal is taken continuous in time. It is multiplied with the impulse train so that we will get a samples of the continuous time signal. And here we have to write the program to verify the sampling theorem practically. So theoretically already we have understood the concept of sampling theorem. Now we will do the programming and we will verify the sampling theorem. So to verify the sampling theorem, we are requiring a software known as MATLAB, Matrix Laboratory. So here we have to write the code for the sampling theorem. So in this verification, first we will draw a continuous time signal. We will draw the graph. And after this, we will apply the sampling conditions. So there will be three conditions. First condition, when the sampling rate is less than twice the maximum frequency, this is known as undersampling. Second condition, when the sampling rate is exactly equal to twice the maximum frequency of the signal. And third, when sampling rate is greater than equal to twice the maximum frequency of the signal. So here we have to draw four graphs of the signal. First graph will be for the continuous time signal. Second graph for undersampling, third graph for exact sampling, and fourth graph for the oversampling case. And here we will come to know that whenever that condition is satisfied, sampling or the discrete original signal can be recovered back from the sampled signal. Okay, so let us come. So in the first case, we will represent a continuous time signal. So to draw the graph for a continuous time signal, we have to define two axes, horizontal axis and vertical axis. Horizontal axis will be the time axis where we will assume any time condition and vertical axis will be the amplitude condition. So let us assume t is equal to, we are assuming t equal to minus 100 to 100. This we have taken as the time. And we have to also define the vertical axis. Okay. So vertical axis means the amplitude. So either we can draw the graph of a sinusoidal signal or a cosinusoidal signal. So we already know how to represent it mathematically. Mathematically, it is represented as x equal to sine omega t or x equal to cos omega t. So here we have to write the mathematical function. So suppose we take x equal to cos omega t. So cos omega t is cos 2 pi f t. So here we have to define the maximum frequency of the signal. So let us assume that fm is equals to 0.02 hertz. We are assuming. So now we have to write the mathematical function to plot the amplitude of the signal. So x is equal to cos omega t. Omega t is nothing but 2 pi fm t. Okay. So this fm and t already we have assumed. And after this, we have to draw the graph. So here we want in one window there should be first should be the graph of continuous time signal, then second graph should be for the oversampling case, then exact sampling case, and then finally the undersampling case. So here we have to fix the position, that in which position we want the graph. So command for that is we have to decide the position, that is the subplot. So subplot, and here we want that a window should open of 2 cross 2 and position is first, at the first position we want. So here we have to write 2 comma 2 comma 1, and now it is a continuous time signal. So here we have to write the command plot horizontal axis versus vertical axis. So horizontal axis t comma x. Okay, and after this here we have to define the parameters, horizontal axis and vertical axis parameters. So here we will write x label, and in x label horizontal axis is time, and then we have to define the y axis. So y label is the amplitude, and after this here we have to give the title. So title of the experiment is, title of this is a continuous time signal, continuous time signal. Okay, so here also if you want we can check the graph of this signal. Okay, so here we have to click on the run option, and then it will ask to save the code, and then we will get the waveform. Okay, so here you can see we are getting the waveform. Similarly for the next case, that is the undersampling case, here we will define fm will be same. Now here we want to sample the signal. So to sample the signal, the condition is small t is equal to n into capital Ts, where capital Ts is 1 upon fs. So small t will be n upon fs. This condition we have to put to sample the signal. So here we have to define the sampling frequency. So fs1 we will take as 0.02, and then we have to also decide the value of n1. The condition is n is equal to, condition is fs is equal to n multiplied by ts, which is nothing but n divided by fs. Okay, so here we have to define the condition. So n1 and fs1 we will define. So n1 we have already taken 0.02, fs1 we have taken, so n1 we will take from -2 to 2. Okay, and then x1 we will decide. So x1 will be equal to cos 2 multiplied by pi multiplied by fs multiplied by fm, 2 cos fm t. So t is nothing but n1 upon fs1. So n1 divided by fs1. Okay, and after this here we have to write the condition x label, y label, and this title condition we have to put. So here you can put x label is your number of samples, y label is amplitude, and this is the title of the title for this is that sampling frequency fs is less than twice of fm. है ना? What is fs? fs 0.02 and fm is 0.02. So twice of fm means 0.04. So fs1 is less than twice of fm. Okay, so this title we have to give. If you want we can run this part of the program. So if you run it you will get this graph, fs1 is less than twice of fm. Okay, similarly after this next we are going to plot the graph for this condition, and here also we have plot the graph. We will put the subplot to decide the condition in which our graph should come. So for that we require the subplot command. Okay, I will just copy the program and we will open it into a new script window. Okay, I will close it, and here we will write the program. Okay, title we have given subplot 2 comma 2 comma 2, and then to plot the graph of the command of the signal, we have to give the command stamp. So it is N1 comma FS1. Okay. So click on the run option. And here you will find the option. It will ask to say so sampling theorem code. Okay, so such type of window will open. And here we have to write N1 comma X1. Okay. And here you can see the two graphs are obtained here. Okay. That was for the first condition and for the second condition. Okay. Here this condition we will give below the code, X label, Y label and title. Okay, run the program. So here you are getting the signal. Okay, now you can go for the next condition. So what is the next condition? So this is the next condition. Fs2 will be equal to 0.04, that is the Fs2, and N2 we will assume as from -4 to +4. And then here we have to write x of 2 is equals to cos 2 multiplied by pi multiplied by Fm multiplied by N2 divided by Fs2. Decide the conditions. So here I will copy this thing and paste here. So here we want 2 comma 2 comma 3 at the third position, and to plot the graph here we will give stamp N2 comma X2 Y label, and here the condition is Fs is exactly equal to twice of Fm. Now run this section. Here we will get the graph. Okay, here we will get the graph. And now the fourth condition. So for fourth condition again we have to assume the parameters. So I will copy it, paste it here. Now for the fourth condition, Fs should be greater than twice the maximum frequency. So here we have to make it Fs3. So Fs3 will be 0.5, and here we have to give the samples. So -50 colon 50 and 2 pi x3. Okay, and Fs3 and N3 we have defined, and here it will be the x3 is equals to cos 2 pi Fm N3 divided by Fs3. Fourth position we want, so 2 comma 2 comma 4, and graph will be plotted between N3 comma x3. And here this is the condition when the sampling frequency is greater than twice the maximum frequency. So run the program, and here you will find the four cases. So first is the graph for continuous time signal. Second case, when sampling frequency is less than twice the maximum frequency of the signal. Third case, when sampling frequency is greater than twice the maximum frequency. And the last case is equal to twice the maximum frequency. And last case, when the sampling frequency is greater than twice the maximum frequency of the signal. So in the last case, you can see that whenever the sampling frequency will be greater than twice the maximum frequency of the signal will be properly sampled and it also can be properly recovered. So this is the overall program. First section, we have plot the continuous time signal. Second section, we have plot the graph for the condition sampling frequency less than twice the maximum frequency. The next section, sampling frequency exactly equal to twice the maximum frequency, and the last section, sampling frequency is greater than twice the maximum frequency of the signal. And here, what we have done, we have just assumed the x-axis and the y-axis. We assume the number of samples, amplitude. So FM and FS. FM is common 0.02 Hertz. FS, we have assumed each for different case. For the first case, FS1 was 0.02 Hertz. Second case, FS2 was 0.04 Hertz. And third case, FS3 was 0.5 Hertz. And we assume the number of samples, N1, N2, N3 for each the case, and fix their position and plotted the graph of the signal. So this is the overall code of this program, and here you can find the output is shown here in the lab manual. And after this is the post lab question, assignment question for the students, which you have to solve yourself. So this is overall about the today's experiment. Thank you all.